And hello there, amazing people, students, lovers of chemistry out there. I'm super excited to be here with you on today's episode of radioactivity, where we've been dealing with different concepts. And this happens to be the third video in the series. And by the way, I want to say a very big thank you to each and every one of you who have engaged with the stuff that I put out consistently out here. And some good news is that we just hit 60 subscribers. I want to say a very big thank you because it will never have been a possibility without each and every one of you engaging with the stuff that I put out there. So let's go even bigger. Let's get this channel to 100 and even 1,000 in no time. All right, now in the meantime, we're going to be looking at the concept of nuclear symbols and atomic notation in today's lesson. Okay, so that's what we want to look at. Let's go into this video and have everything broken down step by step. First things first, understanding how to read and write nuclear symbols is super important when you are studying radioactivity and atomic science. So we're going to be breaking down each concept step by step. We have nuclear symbols, we have the atomic notation, and we're going to be learning about them and seeing how to break them down in simple language and with relatable examples that you can all relate to. So that said, let's get into the first concept that we have for today's lesson. All right, now, so we have the first one, which is the atomic number, mass number, and isotopes. So let's start with the first one, the atomic number. You see, to understand nuclear notations, the symbols that they use, you first need to know three important things. The first one among them is the atomic number. Okay, the atomic number is represented by the letter Z, capital letter Z. Now, the atomic number is simply the number of protons that are contained in an atom's nucleus. Now, an atom, of course, you know, is the smallest part of an element that retains the chemical properties of that element. Now, the atomic number of an atom determines what element the atom is. In other words, every element on the periodic table has a unique atomic number. Unique atomic number simply means that no other element has the atomic number of another one. So we have this example on the screen right now, hydrogen. You can see the element hydrogen over here having the symbol H, and this is the atomic structure of what hydrogen looks like. Now, from this atomic structure, you can see that it shows that it has just one proton and one electron present in the atomic structure. Oh, and by the way, the protons are simply the particles in an atom that are positively charged. So you can see this atom over here, or this particle over here, having a positive charge by the plus sign that has been denoted. That is the proton. And hydrogen has just one proton, which tells us that the atomic number Z will be equal to 1. So that's it for the atomic number. Let's look at the next concept that we need to be familiar with. The next concept is the mass number. The mass number is simply the total number of protons and neutrons that are present in the nucleus of an atom. The mass number simply tells you how heavy the atom is, and it doesn't include electrons. All right, now, so for example, let's say we have the element carbon. Now, carbon has the atomic number 6. Now, let's say carbon has the atomic number 6 and then the mass number of 12. And they say find the number of neutrons that are present in the nucleus. Of course, you know mass number is equal to atomic number plus number of neutrons. And atomic number is simply the number of protons. So if the mass number is 12 for carbon, the atomic number therefore is 6 because we have identified the atomic number of carbon to be 6. The number of neutrons, let's call it X. Therefore, it means X will be equal to 12 minus 6. So the number of neutrons will now be 6. Adding the number of neutrons 6 plus the atomic number 6 will give us the mass number, which is 12. So in summary, the mass number of an element is simply the total number of protons combined with the number of neutrons in the nucleus of an atom, and it tells us how heavy the atom is. All right, now that said, it is time to move on to the next concept, which is the concept called isotopes. Isotopes simply refer to a number of atoms that belong to the same element having the same number of protons, that is, having the same atomic number. Because remember, in the previous slide, we said the number of protons determines the atomic number of an element, but different mass numbers. Different mass numbers means they have different numbers of neutrons. For example, here are two isotopes. We have carbon having a mass number of 12 and carbon having a mass number of 14. How is it possible? It is possible because both of them have 6 protons, but there is a different number of neutrons inside of them. Now look at the first one. In the first case, carbon has 6 neutrons, and you know that mass number is equal to the atomic number plus number of neutrons. So for the first one, the mass number will be equal to the atomic number 6 plus the number of neutrons, which is 6. That gives us 12. That is why we have 12 over here as the mass number of the first isotope. In the second case, the mass number will be equal to the atomic number plus the number of neutrons. The atomic number is also 6, and the number of neutrons is 8, as we see denoted here. 6 plus 8 gives us 14. That is why it has the mass number of 14 over here. So an isotope or isotopes are simply atoms that have the same atomic number but a different mass number. Why? Because there is a difference in the number of neutrons that are present in their atoms. Now think of it this way, because I don't want you to be confused. Isotopes are much like siblings, okay? They come from the same source, which is they have the same parents. The same parents here represent the same atomic number, but they have different body weights, different mass numbers. Now you can see the picture of a family that I have here. We have the parents, the dad over here, the mom over here, which make up the source. They act as the atomic number. But you have the kids over here. You have the little kid, and then you have the bigger kid over here. The bigger kid and the little kid both come from the same source. In other words, they have the same atomic number, but they have different mass numbers, or they have different masses. So even though they come from the same source, their masses are not the same. So that's what the concept of isotopes deal with. Alright, so now that we have talked about the trio of the important concepts you need to be familiarized with when dealing with representing elements, we've talked about the atomic number, the mass numbers, and isotopes. It's time to learn about representing elements using nuclear symbols. Alright, now there is a standard format to write nuclear symbols, or the symbols of elements. Step number 1, we have the letter X. So X here denotes the symbol or the chemical symbol of a random element. It could be hydrogen, it could be oxygen, it could even be uranium. Okay, so when we do not know the element that is being talked about, we use the symbol capital letter X. And then we have the second one, which is the mass number. The mass number is denoted by the letter capital letter A, and it is written as a superscript at the left top corner of this letter X, and it denotes the number of protons combined with the number of neutrons. And then we have the final one, which is the atomic number Z. The atomic number Z is written as a subscript at the left bottom corner of the element, which is X. So this Z over here represents the number of protons that are present in the element or the atom. So for instance, now let's say I have X and then I put the number 6 as this point, and then I put the number 12 at this point. What I am simply saying is that this element is unknown. However, even though it is unknown, it has a mass number of 12. This is its mass number at the top left corner as a superscript, and then it has an atomic number of 6. So it simply tells us that even though we do not know what the element is, we can use the atomic number, which is 6 over here, to identify the element that it is. And on the periodic table, the element that has the atomic number 6 is the element carbon. So we can transform this X into C. So that becomes carbon, which is denoted with the symbol C, and it has a mass number of 12 and an atomic number of 6. This is how we represent elements in the concept of radioactivity using nuclear symbols. Let's proceed into another example. Example number 2 is the element uranium. Uranium in this case is having the mass number 238. So if I were to represent this using the nuclear symbol notation, I would use the symbol U because we know the element that it is. If we had not known, we would have used the symbol X. But in this case, we know the element that it is uranium, and it has the symbol letter U. So we have the mass number, which is 238. So that 238 is written as a superscript placed at the left top corner of the symbol U. At this point, they've told us what the mass number is, and we've denoted it 238. And the mass number, remember, is a product of the number of protons added to the number of neutrons. And then we have the number of neutrons given to us to be 238 minus the atomic number. The atomic number of uranium is 92. You can see it denoted over here. So if I want to represent it in this symbol, I will put 92 as a subscript placed at the left bottom corner of the symbol of uranium. So now that we have the atomic number and the mass number, if they ask us to calculate the number of neutrons, remember, mass number M is equal to protons plus neutrons. Number of protons is the same as atomic number, which is 92. We don't know what the number of neutrons is, so let's leave it as N. The mass number, on the other hand, is 238. If we do a bit of math, N will now be equal to 238 minus 92. When we do a bit of math, that ends up giving us 146. To be a bit simpler, we can do it in a primary school way. This is 238, this is 92. 8 minus 2 gives us 6. 3 cannot minus 9, so we borrow 1 all the way to this point. It becomes 13 minus 9, which gives us 4. And then we have 1 over here, 146. So the number of neutrons present here is 146. Now note, this is an isotope of uranium. There are other forms that uranium can appear in. There is the uranium that has the mass number of 235. So if I were to deal with the second isotope or the second form of uranium, which is uranium having the mass number of 235, remember the atomic number stays the same since it's still the same element. And they ask me to find the number of neutrons present. What would I do? I would simply say the mass number is equal to number of protons plus number of neutrons. The mass number is 235. The number of protons present is 92, which represents the atomic number. Number of neutrons is unknown. So N will now be 235 minus 92. This becomes 143. That will be the number of neutrons that are present in the atom of this isotope of uranium. I trust you're following, and I'm sure this video lesson has been educative for you. If it is, please support my channel by liking, subscribing, and turning on the notification bell icon. So when more videos like this come out, you'd be the first to be notified. Now that we have done all of that, let's proceed into the next concept we want to familiarize ourselves with. We want to talk about writing simple nuclear reactions. All right, we are talking about radioactivity, and we cannot successfully exhaust this topic without talking about nuclear reactions and how they occur. So first things first, it is important to know that when atoms undergo radioactive decay, Radioactive decay, by the way, is also called nuclear reactions. They can turn into new elements by changing their atomic and their mass numbers. So, for example, I have an element called X, and then the atomic number is denoted over here Z, and the mass number is denoted over here A. When this element undergoes a radioactive decay or a nuclear reaction, it can turn into another element that is entirely different. That new element, let me call it Y, and then the atomic number can change from Z to maybe B, and the mass number can change from A to maybe C. So it has changed because it lost some values from its mass number and also lost from values from its atomic number. Now let's see how that happens in the next slide. Let's proceed. So we have example number 1. The first example of a radioactive decay that we have is called the alpha decay. What is the alpha decay? Before we even go into solving any question, the alpha decay is simply a radioactive reaction whereby an element releases an alpha particle. Now remember, in one of the previous videos on this series, we talked about the denotation of the alpha particle. This is how it is denoted. The alpha particle has a mass number of 4 and an atomic number of 2, very much similar to the helium atom. Okay, so now when an atom or an element undergoes a radioactive decay that is the alpha decay, what simply happens is that that element will lose an alpha particle, or it will radiate an alpha particle. What happens, or what that means, is that it will lose a value of 4 from its mass number, and it will lose a value of 2 from its atomic number. So let's solve an example and see how that happens. Alright, so right now on the screen, I have the first example, which is uranium. Uranium having the mass number of 238. So let's denote it. Uranium has the symbol U. The mass number is placed as a superscript at the left top corner, or at the top left corner of the symbol of the element, and the atomic number is placed as a subscript. Remember, we already saw it that uranium has an atomic number of 92. So now we have uranium undergoing an alpha decay. What happens is that after the alpha decay, remember, it will release an alpha particle. An alpha particle has a mass number of 4 and an atomic number of 2. So what this means is that a value of 4 will be lost from the mass number and a value of 2 will be lost from the atomic number. So when we remove 4 from the mass number, which is 238, 238 minus 4 gives us 234. So we have a new element having a mass number of 234 and then having an atomic number of 90, because 92 minus 2 will give us 90. So now the question is, what element has an atomic number of 90? It is the element called thorium, and thorium has the symbol Th. So if I want to represent this equation more professionally, I would write it like this. I have 238 and 92 for uranium undergoing an alpha decay to produce or to radiate an alpha particle having a mass number of 4 and an atomic number of 2, and then plus the new element that is produced. That new element has a mass number of 234 and an atomic number of 90, which is thorium, Th. This is the radioactive equation. Now you can see some points that show the important things that happen in this reaction. First of all, uranium, which has a mass number of 238, becomes thorium, which has a mass number of 234 in this case, and it released an alpha particle. You can see how that happened. All right, now that we have dealt with the first question, let's proceed into the next example. We've seen what an alpha decay is. The next one we want to deal with is the beta or the beta decay. The beta decay is simply a radioactive reaction whereby an element or an atom radiates a beta particle. The beta particle has this symbol denoted here, and the beta particle can either be positive or negative. Now, in the case where it is negative, it has this value as its atomic number -1, and then it has no mass at all. But in a case where it is positive, it has this symbol and has an atomic value of +1 and no mass at all. So in this case, we're going to be dealing with where the beta particle is negative. When it is negative, it is called an electron, and when it is positive, it is called a positron. I trust you're seeing all the concepts, how they're playing out. So first things first, a beta particle is a fast moving electron. You can see it denoted over here. It forms, or it is formed, when a neutron turns into a proton. This increases the atomic number by 1 but leaves the mass number the same. So what they're trying to tell you is that when an element, for instance, let's say X, undergoes a beta decay, it releases the beta particle which has these values, and then what happens is that the mass number, which is a superscript placed at the left top corner, let's say the mass number is A, the mass number will be the same, which is A plus 0. It remains the same, but the atomic number will become Z plus 1, and whatever the symbol of the element is, it will remain the same. All right, so let's solve this example we have on the screen right now. We have the carbon-14 beta decay. So first things first, let's write the symbol of carbon. Carbon has the symbol C, and carbon has the atomic number of 6. And in this case, they've told us the mass number of carbon, which is 14. So when this carbon atom undergoes a beta decay, it releases the beta particle, which has this value -1 as the atomic value and 0 as the mass. Now, remember, the atomic number will now increase by 1, so it becomes 6 plus 1, which is 7, but the mass number remains the same. So the element that has the atomic number 7 is nitrogen, and that is N. So you can see the atomic number here, which is 6, increased by 1 to become 7, but the mass number stayed the same. So here are the points that happened in this radioactive decay. Carbon releases a beta particle to become nitrogen, and then it increased, the atomic number increased from 6 to become 7. I'm sure you saw how the beta decay takes place in a radioactive reaction. So here is a quick summary table to help you recap everything we've been saying since the commencement of this video. We have the first term, which talks about the atomic number. It means, or it relates to, the number of protons present in the atom of an element. And an example we have is carbon. Carbon has the atomic number of 6. So if I were to write the symbol, which is letter C, I would denote the atomic number by writing it as a subscript placed at the left bottom corner of the symbol of the element. The next we have is the mass number. The mass number refers to the number of protons combined with the number of neutrons. And for carbon, we have the mass number to be 14. In this case, if I want to represent the mass number, I will simply put it as a superscript placed at the top left corner of the symbol of the element. So this is telling us that this is the mass number, and this is telling us that this is the atomic number. The next we have is the isotope. An isotope is simply an atom of the same element having different masses. We saw that concept explained using the concept of a family having 2 kids. The 2 kids came from the same source, but their masses were different. So we have the carbon number 12 having the mass number of 12, and carbon having the mass number of 14. So if I were to denote the two of them, I have the first isotope, which is carbon. Of course, the atomic number is 6, and the mass number in this case is 12. And then the second isotope has a mass number of 14, and the atomic number remains the same. These two are isotopes because they are the same elements having the same atomic number but different mass numbers. And that different in mass numbers comes as a result of having different numbers of neutrons. In the first case, the number of neutrons here is 6. In the second case, the number of neutrons here is 8. And then finally, we have the nuclear symbol. The nuclear symbol is simply a short form of writing an atom's information. And this is an example we have over here. Helium. This number 4 over here tells us the mass number, and this number 2 at the bottom tells us the atomic number. So now that we have all of that said, it's time to draw the curtain on this video. But before we do that, let's see some more details on this quick summary table. We have the alpha decay. The alpha decay is simply a process where an atom radiates an alpha particle. In the process, it loses 2 protons and 2 neutrons, or it loses a value of 4 from its mass number, and then it forms a new element. And that example is shown. We saw the example when we saw uranium undergoing an alpha decay. The second one is the beta decay. The beta decay is simply a process where an atom radiates a beta particle, and it happens when a neutron is converted into a proton and then adds an electron to it. And we saw that from the radioactive decay of carbon number 14, where carbon radiated a beta particle to form nitrogen, which has the mass number of 14 and the atomic number of 7. So at this point now, I believe we can draw the curtain on this video. So why does this matter? It matters because understanding nuclear symbols and reactions help us to track how atoms change during a radioactive decay. It helps us understand nuclear energy and radiation, and it helps us to make sense out of topics like carbon dating, nuclear medicine, and even nuclear bombs. Alright, now at this point, we'll be drawing the curtains on today's video. I trust it was educative and informative to you as well. Up next, we're going to be talking about the concept of radioactive decay. I want you to stay tuned for that episode. It will be coming up shortly. Up until then, my name is David, and all I do here is to take the mystery out of chemistry so chemi can make history. I'd like you to subscribe, like this video, and turn on the notification bell icon because we have more and more massive stuff coming your way on this space. I will see you in the next video.